Hello everyone. Now let us move towards the electronic configurations of p block. As we have discussed, in case of p block there are 6 groups, that is starting from group number 13 to group number 18. But out of those 6 groups, the entire p block we are not going to study in a 11 syllabus. In case of 11 syllabus, out of the 6, only 2 groups are there, that is group number 13 and group number 14. So group number 13 and group number 14, that only we are going to study in details in case of electronic configuration from your 11th syllabus. So for group number 13, which are the elements that we are going to see first? In case of group number 13, there are only 6 elements, which are the boron, aluminium, gallium, indium, thallium, and trium. So these are the 6 elements in group number 13. Like that, how many elements are there in group number 14? Again, same, the 6 elements are there in group number 14, which are the, let us see, carbon, silicon, germanium, tin, lead, and uncharacterized. These are the 6 elements in group number 14, and these are the 6 elements in group number 13. So for these 12 elements, we are going to see electronic configuration in terms of p block. So before that, before starting the electronic configuration of these 2 groups, what is the general electronic configuration that we already have discussed in a S block as well as a periodic table? So the general electronic configuration for this 13 group is Ns2 Np1, and general electronic configuration for 14 group is Ns2 Np2. So this is what the general electronic configuration, which is very much useful for us to remember electronic configuration very well and well thoroughly. Because in case of electronic configuration, the most convenient method to know is the condensed electronic configuration. So by using that condensed electronic configuration, we can make a electronic configuration more convenient and more simpler. But for that sake, we also require to have a general electronic configuration. So general electronic configuration is one of the important thing to know. So what is the general electronic configuration for 13 group? It is nothing but Ns2 Np1, and for 14 group it is Ns2 Np2 that we are going to use for the electronic configuration purpose of these elements. But before starting the electronic configuration, again there is a question in our mind. For the electronic configuration, we are having elements, we are having general electronic configuration, but how can we go for the segregating electrons if we are not knowing how many electrons are there? So how do you know the number of electrons, how many electrons are present in that particular atom, just by seeing an atomic number? So first, before starting this point, we have to know the atomic number of all these elements first. So what are the atomic numbers here? The boron has an atomic number 5, aluminium 13, gallium 31, indium 49, thallium it's 81, and uncharacterized it's nothing but 113. Like that. What is the atomic number for the 14 group element? Carbon, it's nothing but 6, silicon 14, germanium 32, tin 50, lead 82, and uncharacterized it's nothing but 114. So now we are having name of elements, atomic numbers, general electronic configuration. So it is more easier for us to go for an electronic configuration of 13 and 14 group. So let us start with the electronic configuration of group number 13. That means the first element of group number 13, which is boron, which has atomic number 5. So can you remember the general electronic configuration and electronic configuration rules of the previous part in case of periodic table and S plot? Because in case of electronic configuration, whenever you are using a condensed electronic configuration, we're supposed to use an inert gas molecules as an inert core. So which are the inert gases first? That we are also knowing that helium, neon, argon, krypton, xenon and radon are the inert gases, and they are having certain kind of inert core which is very much useful for the electronic configuration purposes. So that we are going to use one by one. So now boron is having atomic number 5. So which is the inert gas molecule which has a atomic number less than to the atomic number 5? Yes, definitely. It is nothing but a helium. Helium has atomic number 2. So this can be used as an inert core in terms of boron. Now in terms of aluminium, aluminium has atomic number 13. So which is the inert gas molecule which has an atomic number less than 13, or we can be in before 13, which is nothing but a neon, which has atomic number 10, like that. Here it is argon, which has atomic number 18. Here it is krypton, which has atomic number 36. Here it is xenon, which has atomic number 54. And here it is a radon, which has atomic number 86. So according to that, now we can make an electronic configuration for 13 and 14 group. So let us start by using a general electronic configuration, because in case of this part, here it is in case of boron. Boron is having atomic number 5, and we already have put there an inert core, that is helium inert core, and helium has atomic number 2. So obviously 2 electrons get easily configured by using the inert core helium. So how many electrons are remaining now? Only 3 electrons. So these 3 electrons we're supposed to go for a configure by using a rules. But for the 13 group, what is general electronic configuration? This is ns2np1. So we have to just make it here a ns2 and np1. But what is this n stands for? From the previous part, again we are saying that n is nothing but a period number or a shell number. So what kind of period number is there for a boron? Boron is belonging to a second period. That means how many shells are present in boron? The number of shells are always equal to the number of period. As boron is present in a second period, so boron has only 2 shells. So what is the value of small n then? Yes, it is nothing but a 2. So we can just put a 2 instead of this small n. So this is 2s2, or we can make it a 2p2. So what is the electronic configuration now? Helium, 2s2 and 2p1. Like that we can make a value of n. The same one in case of aluminium, which comes under the period number 3. So what is the value of n then? Yes, it is 3. So we can make 3s2 and 3p1. The same thing we can put here, 4s2, 4p1, 5s2, 5p1, 6s2, 6p1, and 7s2, 7p1. Let us calculate the electron first. Are the all electrons get configured by this rule or not. Helium has 2 atomic number and there are 2s2 and 2p1 in the outermost shell. So 2 electron from 2s, 1 electron from 2p, 2 plus 1 get added 3 and 3 and 2 electrons from helium. So in totality 5 electrons are there. That means we are on the track that we already have configured all the electrons of the helium. But let us we move towards the neon. Neon has atomic number 10. Always remember, neon has an atomic number 10 and 3s2 and 3p1. So from 3s2 and 3p1 there are 3 electrons are coming. So this 3 and neon's 10. So in totality there are 13 elements, 13 electrons. So we already have configured all the electrons of the aluminium over here. But from the gallium onwards, what the things are happening? The atomic number of trapped argon is nothing but 18. What is the atomic number of gallium? It is nothing but a 31, out of which only 18 electrons are there from inert core and 3 electrons are there from the general electronic configuration, that is 4s2 and 4p1. So how many electrons are there in totality? 18 electrons from argon, 2 electrons from 4s and 1 electron from 4p. That means only 21 electrons are there which get configured by this rule. That means still 10 electrons are remaining with the gallium that we have not configured yet. Then what to do now? Because this gallium is in the 4th period and 4th period onwards there are the certain rules for the electronic configuration that we always have to remember. We can put a rule of condensed electronic configuration and general electronic configuration only up to 1st period, 2nd period and 3rd period. But the 4th period onwards we have to make some of the modification in that rule. What are those modifications? Let us see now. In case of 4th period, there is an inert gas, that is inert core, and a general electronic configuration. But between the inert gases core and a general electronic configuration, we're supposed to make a 3D10. Whenever we are in a period number 5th, so in 5th period, in between inert core and general electronic configuration, we have to make a 4D10. In case of 6th period, in between the inert core and a general electronic configuration, we have to put for a 14 and 5D10. And in case of 7th period, in between inert core and a general electronic configuration, we have to put a 14 and 6010. So these are the modification in rules of condensed electronic configuration. That means though we are saying that whenever we are doing general electronic configuration rules applicable for any kind of electronic configuration, so what are we doing? We are just making a general electronic configuration which is follow to inert core. But whenever there is electrons in p block, so always follow some kind of the modification in electronic configuration. That means in case of 4th period element, we can make a 3D10 in between inert core and a general electronic configuration. Same that, put a 4D10 in between inert core and general electronic configuration of 5th period, put a 4F14 and 5D10 in between inert core and general electronic configuration of the 6th period, put a 5F14 and 6D10 in between inert core and general electronic configuration of the 7th period. Like that, now we can again calculate the number of electrons and let us check whether all the electrons by this modification get configured or not. Let us now see. In case of gallium, there are atomic number is 31. So out of 31, 18 electrons are from argon, 2 electrons from 4s, 1 electron from 4p. So 2 plus 1, 3, 3 and 18 are 21, and this 10 electrons from 3D. So 21 plus 10, 31 are there. That means we already have configured all the electrons of gallium. Let us move towards the indium. Now in case of indium, the atomic number is 49. And what is the atomic number of this krypton, which is showing a inert core? Krypton is having atomic number 36. So 36 here, 2 here and 1 here. So 36 and 3 are the 39 and 10 electrons from the 40. So it is 49. That means we are configuring all the electrons. Now in case of thallium, the atomic number of thallium is 81 and we are using xenon as the inert core. What is the atomic number of xenon? It is nothing but a 54. So 54 from the xenon inert core, 2 from the 6s and 1 from the 6p. So 2 plus 1, 3, 3 and this 54. How many are there? 57 electrons are there, but we need to have 81 electrons because 81 is the atomic number of thallium. So out of 81, we are configuring only 57. So how many are remaining now? There are remaining 24 electrons. That 24 electrons are coming from this 4f, 14 and 5d10. Along this electronic configuration, we can fulfill all the electronic configurations. The same things is also happening with the ununtrium. In case of ununtrium, the atomic number is 113, in which radon is giving 86 electron, 7s is giving 2 electrons, 7p is giving 1 electron, and in between 24 electrons are given by this 5f14 and 6010. So like that, by using this modification, we can make the electronic configuration more simpler in terms of p block element. But this is what the electronic configuration of 13 group that we have finished right now. But let us move towards the 14 groups electronic configuration. But always remember, if you get thorough in an electronic configuration of 13 groups, so there is no any difficulties to come in case of 14 group electronic configuration, because the reason, the consequences and the properties are exactly same as per the 13 group electronic configuration for the rest of the groups. So let us make a move towards the 14 group electronic configuration and see whether is it same as to the 13 group or not. Let us see now. Now in case of 14 group, the first element is nothing but a carbon. Carbon has atomic number 6. So 6, that means 6 electrons are there to be configured. Now which is the inert gas which can produce an inert core for this 6? Yes, there is a helium which has an atomic number 2. So we can make a helium inert core. Like that, we can make a move towards the next inert gases. So we can make here a neon, here it is argon, here it is krypton, here it is xenon, and here it is radon. So this is what the sequence of inert core in case of 14 group, which is nothing but same as to that 13 group. Just by having a look of this two part, we can say that there is very much similarities in the inert core of a 13 and 14 group, and also this is going to move forward for up to the 17 and 18 group also. So after this inert core, what we're supposed to include in electronic configuration? We're supposed to include this now general electronic configuration. What was it in the 13 group? It is ns2 np1. And for 14 group, what is it? It is nothing but a ns2 np2. So we just have to make here a ns2 np2 instead of ns2 np1 of the 13 group. So how the things are happening now, let us see. But for the case, in case of again general electronic configuration, there is a letter small n. What is it stands for? As we already have discussed in the group number 13, n is nothing but a number of shells, or we can simply say it as a number of period. Carbon is belonging to the second period, so the number of small n is nothing but a 2. So we can make it here 2s2 and 2p1. Is it the simpler one? In case of ns2 and np2, Is it the simpler one? Because in case of boron, helium, Ns2 and P1, given the electronic configuration of boron in terms of 13 group according to the general electronic configuration, but in case of carbon, which is having atomic number 6, how many electrons are there? 2 from 2p, 2 from 2s and 2 from helium inert core. That means 6 electrons are there, get easily configured by this rule of 14 group. But now next one, that is silicon, which is having 14 electrons in it. 10 electrons are coming from the neon. So how many electrons are remaining? Obviously only 2 electrons are remaining, which are coming from the general electronic configuration. So what is the general electronic configuration for the next element? It is 3s2 3p2. So 2 electrons from 3s, 2 electrons from 3p and 10 electrons from neon. So in totality 14 electrons that easily configured. But again there is a question as we are making a move towards the 4th period. Because as per the 13th group, we already have discussed that whenever we are starting electronic configuration of a 4th, 5th, 6th and 7th period, there is supposed to be some modifications. So what kind of the modification that we are again going to see in a group 14 also, as germanium having atomic number 32 and this is nothing but a part of 4th period. So in case of 4th period, always we have to make some modification between general electronic configuration and inert core. Inert core we already have put there. That means for 32, what is the inert core? Argon inert core is there, and what we are going to put further, nothing but a general electronic configuration, that is 4s2 4p2. But as per the modification in group number 13 that we already have studied, in case of period 4, in between this general electronic configuration and inert core, we have to make another entry, that is 3d10. So let us make an entry over here and let's calculate whether the elements get completely configured or not. What was the atomic number of argon? It is nothing but 18. 2 electrons from 4s and 2 electrons from 4p. So in totality 18 plus 4, 22 elements, electrons are there. This 22 electrons, and for this 10 electrons of this 3D entry, 22 plus 10, 32 electrons are there. That means germanium get easily configured completely. That means this modification that we had studied in group number 13 are not restricted towards the group number 13, but they are fulfilling all the parameters in case of all the groups of p block element. That means it is very much easier for us now that we can make the electronic configuration of remaining elements of the 14 group just by using this modification also. So without hesitating, just go for this modification. So now this is group number 5th. So we can make here a 5s2, 5p2. This is 6. So this is 6s2, 6p2. Here it is 7. So 7s2, 7p2. And what were the modification that we are going to put over here? This is 3d10, so this is 4d10, this is 4f14 and 5d10, this is 5f14 and 6d10. Let us we calculate once to know whether they have configured well or not. What is the atomic number of lead? It is 82. How many electrons are coming from xenon? 54. So 54 and this 4. 54 and 4 are nothing but 58. 58 and this 10 are nothing but a 68. 68 and 14 are nothing but 82. That means we are completing the entire configuration of p block elements of group 13 and group 14 elements by using a condensed electronic configuration rule and by using a general electronic configuration rule, but by using some kind of the modification in those elements which are coming from the period number 4th, 5th, 6th and 7th. I just remind you what are the modification. The modifications were 3d10 in case of period number 4, 4d10 in case of period number 5, 4f14, 5d10 in case of period number 6, and 5f14 and 6d10 in case of period number 7. These modifications have to be made in between general electronic configuration and inert core to know and to ensure the smooth electronic configuration of a p-block. So by using these rules, we can make an electronic configuration of any elements of a periodic table very well. So this is what the electronic configuration of few of the elements, that is elements from group number 13 and group number 14, which are enlisted in your 11th syllabus. Thank you.